So find the DFT of the sequence. X of n is equal to 1 1 1 0 0 0 0. So here, if you look into the length of the sequence, the value of the length of the sequence n is equal to 8 here. So it's a 8-point DFT, and we need to find out the 8-point DFT. So let us write the generalized formula for finding the DFT. So the DFT of x of n is nothing but it's a x of k. So the formula is summation. We have the formula summation n is equal to 0 to the n minus 1 x of n into omega n to the power of kn. So here k can take the value from 0 to the n minus 1 it will take. This is a generalized formula. Now let us substitute n is equal to 8 in this one. So we'll get x of k is equal to summation n is equal to 0 to the 7 x of n into omega a to the power of k into n. If we expand the formula for n is equal to 0 to the 7, so we can substitute the values for the x of n. We can do substitute here. X of 0 is equal to 1, x of 1 is equal to 1, 2 is equal to 1, 3, and so on. We can do substitute by expanding this summation. Let us expand the summation here. So here we get x of k is equal to, if I substitute n is equal to 0 here, we get x of 0 into omega a to the power of 0. So x of 0 is nothing but its value is nothing but 1. This value is equal to 1. Directly I am going to substitute here. So it is 1 plus, for x is equal to 1, it is x of 1 is 1 into omega a to the power of the value of n is 1. So k will remains like that only. Next, for n is equal to 2, so it is 1 into omega a to the power of 2 into k. Next, is equal to 3, it is omega a to the power of 3 into k. Next, for n is equal to 4, it is 0, 5, 0, 6, 0, 7, 0. So we can substitute as, for n is equal to 4, it is 0, 5 it is 0, and 6 also it is 0, and 7 also it is 0. So this is the value of x of k we got. Now we can substitute the value of k from 0 to the n minus 1. That is, we can substitute the value of k. 0 is less than k is less than or equal to the 7. We can substitute because the value of n is 7. Sorry, n is 8. 8 minus 1 will be the 7 we'll get. Now, in order to find, if I substitute k is equal to 0, we get the value. So before that, we need to find the values for the Twiddle factor. In the last session, we have seen in how to find the values for the Twiddle factor. Let us write the values for the Twiddle factor here. So it is, we done the calculation. Omega a to the power of 0 is equal to omega a to the power of 1. The value for the omega a to the power of 1. So this is equal to the, it is 1 by root 2. 1 divided by root 2 minus j into 1 divided by root 2. This is omega a to the power of 1. And for omega a to the power of 2, this will be, it is minus j. And omega a to the power of 3, omega a to the power of 3. So this value will be the minus 1 by root 2, minus 1 by root 2, minus j into 1 by root 2. And for omega e to the power of 4, so this is minus 1. And as we see, one of the symmetry property, so if you know the half of the values, remaining half values we can find out. That is, by applying the symmetry factor property of the Twiddle factor, we can find the remaining values for the Twiddle factor. We can find out here. So omega e to the power of 5, so it is nothing but we can express as omega e to the power of 1 plus 4 we can express. So that is omega minus omega e to the power of 1. So if I multiply minus to the this one, we'll get the value for omega e to the power of 5. So that's the advantage of the properties. So it will be useful for reducing number of calculations. So j divided by 1 by root 2. This is for omega e to the power of 5. So similarly, for omega e to the power of 6, will be like this. Omega e to the power of 6 is nothing but it's a minus 1 into that is we can express as a 2 plus 4. That is minus omega e to the power of 2 we can write here. So minus into minus will become plus j will get. So plus j omega e to the power of 6 will be omega e to the power of 7, which is nothing but minus of 3. So it is 1 by root 2 minus into minus will become plus j divided by root 2 will get here. So these are the values for the Twiddle factor we got here. So by making use of these Twiddle factor values, let us find out let us substitute k is equal to 0, 1, 2, 3, and let us find out the values for the x of k. We can do substitute here. So what shall we do? Let us substitute k is equal to 0 in this one. So let us substitute k is equal to 0. So it will become x of 0 will get here. When I substitute k is equal to 0, wherever k is there, here wherever k is there, here k is there, here also k is there, and here also k is there. So wherever k is there, we can substitute as 0. So if omega e to the power of 0 is nothing but 1. So it is 1 plus 1 plus 1 plus 1, it will become equal to the 4 will get here. So similarly, let us substitute k is equal to the 1. So it will become x of 1 is equal to 1 plus omega a to the power of 1 plus omega a to the power of 2 plus omega a to the power of 3. So if you substitute these values, so we'll get, and if we simplify, omega a to the power of 1 is already we calculated the values for the Tweedle factor here. So this is the values. And if omega a to the power of 2 is minus j and omega a to the power of 3 is, it is the value minus 1 by root 2. The value is here minus 1 by root 2 and minus j into 1 by root 2 is here. So if I substitute all those values, so x of 3 will become 1 minus x of 3, x of 1 will become, it is 1 minus j into 2.414 will get. So similarly, let us substitute k is equal to the 2. So it has become x of 2 is equal to the, wherever k is there in this expression, let us substitute k is equal to 2. And here also let us substitute k is equal to 2. So it has become 1 plus omega a to the power of 2 plus omega a to the power of 4 plus omega a to the power of 6. So if you evaluate this one by substituting the corresponding values, so it will become equal to 0 will get. So similarly for k is equal to 3, it will become wherever k is there. So we can substitute that as 3. So 1 plus omega a to the power of 3 plus omega a to the power of 6 plus 3 into 3, here omega a to the power of 3k is there. So 3 into 3 will become 9. So omega a to the power of 9 can be written as, by applying the periodicity property, we can write that one as omega a to the power of 1 plus 8. So we can rewrite as a omega a to the power of 1 we can rewrite here. So that is the advantage of the applying the periodicity property. So which is exceeding the value behind the value of n. So we can apply the periodicity property and we can do simplify. Now x of 3 value. So if you simplify by substituting the Tweedle factor values, it will become 1 minus j 0.414 will get here. So what are the values we'll get? Let us highlight these values here. So we got 1 minus j 0.414 we got here. So similarly, let us substitute k is equal to the 4 here. So it will become x of 4 is equal to the 1 plus omega. Okay, wherever the k is, we can substitute 1 plus omega to the power of 4 plus omega e to the power of 8 plus, so this is 2k, and for example k is equal to 3. If I substitute here, so 4 3 is a 12, it will become omega e to the power of 12. So omega e to the power of 8 is nothing but it's a omega e to the power of 0, and omega e to the power of 12 is nothing but it's omega e to the power of 4. So by applying the periodicity property we can do calculate. So if you simplify, this value will become equal to the 0 we'll get here. So similarly, let us substitute k is equal to the 5. So x of 5 is equal to 1 plus omega e to the power of 5 plus, for k is equal to 2, omega e to the 2 into 5 will become 10. For omega e to the power of 3k, so if I substitute k is equal to 5, it will become omega e to the power of 15. So here omega e to the power of 10 is nothing but, so 8 plus 3, it is omega e to the power of 3, and this is nothing but omega e to the power of 7. So if you do substitute here, so and if you simplify, it will become 1 plus j into 0.414 will get here. So this is the value for k is equal to 5. And similarly, let us substitute k is equal to 6. So it will become x of 6 is equal to the, so wherever the k is there, we can substitute here omega to the power of k into, that is 1 into k value 6, it will become omega to the power of 6. Next omega to the power of 2k is there, it will become 12. Next omega to the power of 3k is there, it will become 60 is 18, it will become. And omega to the power of 12, we can applying the periodicity property, it can be obtained as omega to the power of 4. And this one we can write as omega to the power of 8 minus 18 will be 10 will get. Again apply the periodicity property, it will become omega to the power of 2. So if you simplify by substituting the values, this will become equal to the 0 will get. So similarly, let us substitute k is equal to the 7. So it will become x of 7. Wherever the k value is there, it is substitute omega to the power of 7 plus omega to the power of 14 plus omega to the power of, so 21 will get. So this will become 21 will get 21, and omega to the power of 14, which is also nothing but omega to the power of 6, and omega to the power of 21, it is nothing but omega to the power of 8 minus 21 will be the, so 13 will get, again in my subtract here, so 30 minus 8 will be the 5 will get. So by substituting the Tweedle factor values, so it will become 1 plus j into 2.414. So these are the values of the x of k we got here. So we got the values. So that is for k is equal to 0, we got 4, and k is equal to 1, 2, k is equal to 3, 4, and 5 here. So that's in the frequency domain also for the Fourier transform, that is discrete Fourier transform, the values will be discrete in nature. So let us summarize the values for this x of k. So let us write, once we find the values, let us summarize the values. So x of k is equal to for k is equal to 0, we got 4, and for k is equal to 1, it has we got 1 minus j 2.414. For k is equal to 2, it is 0. For k is equal to 3, so 1 minus j into 0.414. For k is equal to 4, we got it as 0. So it's a 0 is here. 0 is here. Next, for k is equal to 5, it has, for k is equal to 5, we have 1 plus j 0.414. So 1 plus j 0.414. Next, for k is equal to 6, it is 0. For k is equal to 7, it is 1 plus j 2.414. So these are the values for the x of k we got here. So we can see verify here. So here this is the value for k is equal to 0, 1, 2, 3, 4, 5, 6, and 7 we got here. At k is equal to n by 2. K is equal to n by 2 means the value of n is 8. So 8 by 2 will be the 4. So this is the location for that one. So this is the location for that one. This is the location for the k is equal to 2 here. So at the center point, there is one property which is called as a symmetry property. Suppose if x of n is a real sequence, so you can see this x of n, we can see it here. So the x of n is a real sequence, what we have seen here. So it does not contain any complex quantity. So then it's a DFT, that is x of k is going to satisfy the symmetry property. The symmetry is like this here. At k is equal to n by 2, it is going to satisfy the symmetry like. If you take the conjugate of this one, we'll get this one here. For example, if I take the conjugate of this quantity, that is conjugate of minus j will become plus j, so it will become 1 plus j 0.414. And similarly, if we take the conjugate of 0, so it will become the other quantity we'll get here. So this is nothing but obtain the conjugate here. So similarly, if we take the conjugate of this one, so we'll get k is equal to 7 we'll get here. So then we can verify whether the answer whatever we got, whether it's a correct or not, by taking the conjugate and by applying the property that is called as the symmetry of the real sequences. So like this, we can find out the DFT of the any real sequences we can find out by applying the formula and by finding the values for the Twiddle factor. So in the next session, we'll see how to find out the IDFT of the sequences, and we'll take some problems and let